Hello, quick video on hypothesis testing and sample means. So quite often we'll have a sample and we're interested in whether that sample came from the population. Example I'm going to use is the heights of sixth formers, male sixth formers, and we may be measuring over recent years so we know what that distribution looks like. And then we take a sample of this year's students. We're interested in whether the heights changed. Okay, so in these circumstances, once again, we're going to make use of these extremely useful properties about samples and their means and standard deviations. So the mean of sample means is going to be the population mean, but the standard deviation of sample means is going to be the population standard deviation over root n. Now, if we're testing whether the sample comes from a population, this is classic hypothesis testing world, and we're going to compare the sample mean with the population mean, and we're interested in doing that in terms of standard deviations, and we're going to assume it's normally distributed as most of these are. So our test statistic, which I'll go into in a bit more detail in a minute, it's going to be that distance between the two, sample mean and the mean, divided by the standard deviations. And that standard deviation is the sample mean, so that's sigma p over root n. And our approach to this is that we're working on the basis that the sample does come from the population, so H0 is based on the known population statistics. Okay, so our hypothesis test that we're going to apply in this situation, well, H0 is that the sample comes from the population, so we can use all the statistics for that. H1 depends on the context. We might be interested in whether the sample is just different from the population. It might be that we're interested in higher, so are students getting taller, or is it lower, are students getting shorter? And our test statistic that we're going to use for Z, because then we can do all our calculations on the basis of normal distribution, is our sample mean, take away our population mean, i.e. the distance between the two, and then we're going to measure it in standard deviations, and we know that the standard deviation of the sample is sigma p over root n, because what we're basically doing is modelling our sample means as being normal, with the mean being at population mean and the standard deviation being sigma p over root n, which we'd write as a square in here as a variance, don't we, in the normal. And then we're going to use our probabilities from our normal distribution to compare it with our significance level to make a decision. Okay, so let's have a look at our example here. In recent years, the heights of male sixth form students is distributed with a mean of 173.5 centimetres and a standard deviation of 6.49. And if we take a sample of 5 of this year's students, we can see whether we can look at whether or not the heights changed. So first student 170.1, second student 172.2, and the final student's 168.9. So the mean of that sample is therefore 173.38. And what we can do is compare that against our population. Here we've got that mean and standard deviation. So our Z statistic is 107, our sample mean of 173.38, take away our population mean of 173.4, and then we've got to look at our standard deviation here for the sample, which is going to be our population standard deviation over root 5, which is I think that's 2.9, I think that worked out to be. And so our overall Z value is going to be minus 0.041 standard deviations. Okay, so using our, if we want to find that from our normal distribution, what the probability is that fits with that Z value, we can look it up in our tables, looking for our phi value, or in our calculator. For our Z is 0.41, right, that's minus. So we'd be doing a 1 minus to get our positive value here, wouldn't we? So in the table we get 0.56 for that Z value, and so our probability is 0.48 in its extreme end. That's 48%. That's not very extreme, is it? And against any measure like 5% or 10%, that's not significant. Okay. To be, we could look at what values would need to be significant. So let's have a look at significance level of 5%. Let's assume it's just going to be different for this purposes, and we're going to do a two-tailed test. So the critical value in terms of percentages will be 2.5%. So that's the 5% halved. Therefore, we're interested in our Z value that's going to give us that phi there of 0.975. And as we know, that one is 1.96 standard deviations, isn't it, the Z value? So looking at our critical values then, we can find our critical values as being our mean, plus or minus the Z, the 1.96 above, to our standard deviation. So our mean, population mean here was 173.5. There's our 1.96. Here's our standard deviation of our sample, which is, that one's 2.9, isn't it? So 1.96 times 2.9 gives us 5.3. So we're interested in 173 plus or minus. It's got to be more extreme than plus or minus 5.7. So therefore, our critical regions are, our critical values. Critical values are 167.8 and 179.2, and our critical regions are below 167 or above the 179 value, so right out on the tails. That's what we'd have to have in our sample for something to statistically changed. Okay, here's our my quick summary here of the topic. So we can hypothesis test a sample, see whether it comes from the population by using a test statistic based on the sample mean and the population statistics. So our Z value is therefore going to be the sample mean. Distance of sample mean is away from the population mean in terms of standard deviations of the sample means, which is sigma p over root n, because our sample mean is distributed normally with that mean, pop mean, and standard deviation sigma p over root n. We can calculate the probabilities from the normal distribution and compare probabilities again that way, or we can do the critical values by working the calculation the other way around from our significance level into our Z value, and it's going to be our mean plus or minus the Z times our standard deviation, the population over root n. So there we are. I hope that's of use.